All right, guys, welcome back. Moving on from our quick study of factorial, which will play a part in the next couple of lessons. We start section 8.4, which you can see is entitled the binomial theorem. And basically what it is how do you take a two-term binomial and raise it to a power that maybe gets larger than what is convenient. You guys have done this already with powers like 1, 2, and 3, but you haven't really gone beyond that and tried raising a binomial to, say, the 4th, 5th, 6th, or even like the 20th power. The reason it's in this chapter is that, like with sequences and series, there's a lot of number patterns that are noticeable and will help you with a shortcut in getting the answer. So to start off here, I've listed off some of the lower binomial expansions. You can see that anything to the 0 power is 1, and obviously anything to the first power is just itself. And then, you know, from past math classes, multiplying that answer by another a plus b, you know that a plus b squared is a squared plus 2ab plus b squared, and so on and so on. Okay. What you would probably agree with is that the first three, raising it to the 0, the first, and the second power, really no big deal. You just obviously use the powers of 0 or 1 or FOIL to do a plus b squared. Somewhere in the neighborhood of doing it to the 3rd or the 4th power, you would agree that it starts to become cumbersome. It becomes long, and the possibility for mistakes increases. So imagine then what the difficulty would be if you had to raise it to the 5th, 6th, 7th power, and so on. So our study today is trying to figure out what are some shortcuts if we were asked to raise it to even the 4th power or 5th, 6th, 7th power. And it's going to take us a couple sections or a couple lessons to get through both sections or both parts of section 8.4. So this is just going to be the first part and a couple of shortcuts. What I'd like you to do is just kind of look at the answers there for the first 4 powers of a plus b and notice some patterns. Okay, these are patterns that you're going to want to recognize and then carry through for the shortcut. If you look at the first variable a, it always starts at the highest power, whatever you're raising the binomial to, and then it decreases by 1 in each term until to the last term where that variable doesn't exist at all. And then vice versa, the second variable, in this case b, is non-existent in the first term, but then increases by 1 power in each successive term until the very last term where it's at its highest. So the first variable decreases in power 1 at a time, and the second variable increases by 1 power at a time. You can also see, if you took a good look, that if you looked at each term and added together the exponents of a and b, you would always get the same number, no matter which term you're looking at. For example, if we looked at a plus b to the 4th, obviously the first term, it's a to the 4th. If you look at the second term, there's an a cubed and a b. So that's 3 and 1, so that's 4. In the third term, there's a squared and a b squared. 2 plus 2 is 4. Okay, so the sum of the exponents for each of the variables will always add up to equal the same as the original binomial expansion. So if these patterns hold true, and we neglect the coefficients, we could predict what the variables would be and what their exponents would be on them, even for something as high as x to the 7th. So follow along if you can. You know the first term is going to be x to the 7th. The second term is going to have a coefficient in it, but you can see that it's going to be x to the 6th. And then there's going to be a y. The next term is going to be an x to the 5th and a y squared. The next term is going to be an x to the 4th and a y cubed. Next term is going to be x to the 3rd and a y to the 4th. And it'll keep going, and I'm going to run out of room here, but you get the idea. The next term would be x squared and y to the 5th. The next term would just be x and y to the 6th until you get to the very last term, which is just y to the 7th. So you can see that it went, for x, it went 7, 6, 5, 4, 3, 2, 1, 0. And for the y variable, it went 0, 1, 2, 3, 4, 5, 6, 7. If you want, you can put in the exponents of 1 on the variables that don't have an exponent, but again, it's understood to be a 1. Okay, so that is how easy it would be to produce the variables and their exponents. The next step would obviously be to find a shortcut for producing the coefficients. And if we can get the coefficients combined with the exponents on the variables, we'll have everything we need. So the trick is to take each of the answers from the previous page where we had all the powers, a plus b to the 0, a plus b to the first, a plus b to the second, and so on. And what you're going to notice here, I'm going to try to squeeze this in, you're going to notice that if you put in exponent or coefficients for all the ones that are missing, you're going to see 1s there, 1s all the way on the outer edges. And if you took a good long look, you could see that the next row could be produced. Obviously, the variables and the exponents are very similar to what we just did, but let me just show you and see if you can catch on. So it's going to be a 1. And then what we do is we take the two terms that are right above to find the next term. So we got a 4 and a 1, bring that down, and it's going to be a 5. And obviously going to be a to the 4th b. You got a 4 and a 6, put those together, and you get 10. And that would be a cubed b squared. You got another 6 and a 4, so that's a 10. A squared b cubed. Got a 4 and a 1, and that's a 5. Whoops. A b to the 4th. And then, of course, the last term is always going to be a 1. It'll just be the b by itself. Okay, now, that wasn't the best illustration, but what you'll see is that down the left diagonal and down the right diagonal, you're always going to get coefficients of 1. To get the next terms, you can look at the line above it and add the two coefficients that are sort of right above. For example, we did a 1 and a 4 to get the 5, a 4 and a 6 to get the 10, a 6 and a 4 to get the 10, a 4 and a 1 to get the 5. And what you're soon going to produce is what they call Pascal's triangle. So I'm going to do the next row, but I'm only going to do the coefficients. So we're going to ignore the variables. We can always plug those back in later. So the next row would have coefficient of 1, and then 5 and 1 is 6, 5 and 10 is 15, 10 and 10 is 20, 10 and 5 is 15, 5 and 1 is 6, and the last one's always 1. Okay. So what you can use for the coefficients is what they call Pascal's triangle, and you always just start with a 1 and then put two 1s down for, so that would be the 1 would be a plus b to the 0 power, the 1 and the 1 would be what a plus b to the first power is, and then you can just keep really easily produced by just adding the two numbers that are above and writing it in the middle. Okay, and obviously you could keep going for as high as you wanted to go. This is just, would get you up to maybe doing a plus b or x plus y to the 6th power. Pascal's triangle is great, and you can probably stretch it out another row or two to kind of get you shortcut coefficients for anything maybe up to the 7th, 8th, or 9th power. But even at that, that's probably where Pascal's triangle starts to lose its convenience. You don't want to go much past that. We're going to need a different shortcut for that. But some of the observations you should be able to make is that Pascal's triangle is symmetric. In other words, the numbers, as they go up, come back down the same way. The second number equals the n, whatever you're raising the binomial to. So if you're doing a plus b to the 7th power, the second number in the row would be a 7. And maybe the other thing you should recognize from both Pascal's triangle and our variable work is that there's always n plus 1 terms in a binomial expansion. What I mean by that is if we're raising something to, say, the 5th power, you can see in Pascal's triangle, we find the row that's got a 5 in it, and you can see there's 1, 2, 3, 4, 5, 6 terms. There's 6 coefficients, which means there's going to be 6 terms. So there's always going to be one more term than whatever power you're raising it to. And as I said earlier, most people, most teachers, most math books would agree that Pascal's triangle is a great way to shortcut to find the coefficients, as long as the exponent isn't getting much bigger than, say, 7 or 8. 9's probably a stretch. And when we get to powers bigger than that, I will teach you another shortcut that will come in our next lesson. All right, so let's try to put all this together and see if we can't do a few examples here. Now, what I would encourage you to do is write out Pascal's triangle on a sheet of paper. Make sure you get it right. You don't want to have the wrong Pascal's triangle. That means every answer is going to be wrong. But use that Pascal's triangle for the coefficients, and then just use your properties with the exponents. And you can do it one term at a time, or you can maybe do the coefficients and then come back and do the variables, however you want. I'll show you one way of doing it that's worked for me, and then we can see if it would work for you as well. So I'm going to take a quick peek back up here and see my row for 6th power. Okay, so it is 1, 6, 15, 20, 15, 6, and 1. Okay, so we know from Pascal's triangle those are going to be the exponents, the coefficients for this binomial expansion. I like to do it one variable at a time, so if you start with x, you could say, all right, it's going to start with x to the 6th, it's going to go to x to the 5th, x to the 4th, x cubed, x squared, x, and then in the last term there will be no x term. And then, obviously, with y, start with nothing in the first, then it's going to be y to the 1st, y to the 2nd, y to the 3rd, y to the 4th, y to the 5th, and y to the 6th. And that's how easy this can be if you just combine Pascal's triangle with your properties of the exponents. And again, just check. I got x to the 6th, 5 and 1, it makes a power of 6, 4 and 2, 3 and 3, 2 and 4, 5 and 1. So the sum of x and y always adds up to be 6. The symmetry's there with Pascal's triangle numbers. And since this is a sum, a binomial that's got a plus sign in it, all the signs are going to be plus. Again, your choice if you want to write the 1 as the coefficients in the first and the last term, but it's kind of useful to start with that just so you can use Pascal's triangle. Okay, so a little change of pace here on the second one. You can see that it's got a minus sign in it. Okay, so we have to deal with that. And we can also see that one of the terms is 2a. So anytime your first or your second term of the binomial is not just a variable by itself, it's going to be a little tougher. Okay, so you got to be a little more patient with it. So again, let's look back up here, and I can see I've got a Pascal's triangle row that says 1, 5, 10, 10, 5, and 1. So there's your coefficients from Pascal's triangle. The minus sign indicates, and there's different ways to do this, but if you really want to know how to just cut to the chase, it means the signs are going to alternate. So it'll start positive, the second term is going to be negative, the third term will be positive, negative, positive, negative. That way you can just plug in 2a and b instead of having to try to plug in a negative b. So the tough part on this one is going to be the 2a. We're going to have to take the 2a and raise it to the 5th power on the first term. In the second term, it's going to be 2a to the 4th, 2a cubed, 2a squared, 2a, and 2a won't be in the last term. Okay, no b in the first term, b to the first, b to the second, b to the third, b to the fourth, and again I'll bring back that 1, and it would be b to the fifth. Okay. Always gets a little crazy here in terms of making sure you have enough room. I'm going to clean this up just a little bit so you guys can see it a little better. Okay, the complicating factor here is the 2a. We're going to have to raise 2a to these powers, and that is probably the hardest part of these binomial expansions, is making sure that you get it set up right. I'm going to give you most of the credit if you do this, and then to get the final answer, you're going to have to do some simplification. For example, this 2a to the fifth would be 2 to the fifth power, which is 32a to the fifth. 2 to the fourth is 16, and 16 times a negative 5 would be a minus 80, a to the fourth b. 2 cubed is 8, and 8 times 10 is 80, a cubed b squared. 2 to the fourth is 4, 2 squared is 4, so times 10 is going to be negative 40, a squared b cubed. And this one would just be straight multiplication, so plus 10 a b to the fourth, and minus, you can just say 1 or just b to the fifth. So the coefficients aren't always going to stay exactly what you get from Pascal's triangle, especially if either one of your two terms in your binomial has a coefficient in itself. So be really patient, put it in parentheses, and then consequently raise it to the power, and the coefficients are going to look a little different than Pascal's triangle. That's probably going to happen in a good portion of your problems. And for our last example here, we'll look at one where either the a or the b term actually has exponents itself. So again, we'll cheat. We'll go back up here. We'll look at the fourth row of Pascal's triangle. And it was a simple one. It's just 1, 4, 6, 4, and 1. Easy enough. It's a plus, so everything's going to be a plus. We're going to start by taking x squared. Whoops. X squared, and we have to raise that to the fourth power. In this second term, we're going to do x squared to the third. And this term, we're going to do x squared to the second. Do x squared to the first. And then obviously no x squared in the last term. For the y, there's no y term in the first. Okay, so now we've got y cubed to the first, y cubed to the second. Again, I didn't leave myself enough room, so we'll move this. It'll be y cubed to the third, and then it was plus 1, and it'll just be y cubed to the fourth power. Again, if you want to check it, you can just do your x squared. It's to the fourth, third, second, first, and then no term. And for y, it's not in the first term. It's y cubed to the first, y cubed to the second, y cubed to the third, y cubed to the fourth. Now all you got to do is just kind of simplify this using your laws of exponents. So x squared to the fourth power is x to the eighth. We're going to have a coefficient of 4. It's going to be x to the sixth, y cubed. You're going to get 6x to the fourth, y to the sixth. Remember, when you raise a power to a power, you multiply exponents. So plus 4x squared, y to the ninth. And the last term would just be y to the 12th. Okay, and you can see in this example that even though the powers won't add up to equal 4 anymore, because there was x squared and x to the, or y to the y cubed in there, you will see some symmetry. It goes 8, 6, 4, 2 for the exponents on x. It goes 0, 3, 6, 9, 12 for the exponents on y. Again, 3 examples there. You can see maybe an easy one, medium, and difficult. And if you're just kind of patient with it and use Pascal's triangle for the coefficients, and then use the decreasing and increasing values for the exponents on your first and your second terms, it should be something that is pretty systematic in a way. And again, if you show me your work, I can give you a lot of credit for the intermediate step. And then if you make a mistake going to the simplification, not the end of the world. Okay, and maybe take off a few points. Okay, hope that helps. There'll be an assignment for that, and we will probably make that due on Monday. Thanks.